Scientists have been watching the heart of the Andromeda Galaxy flicker with bursts of X-ray light that shouldn't exist. A black hole, by definition, is supposed to be dark, a gravitational void that swallows everything, including light itself. But 2.5 million light-years away, at the center of our nearest large galactic neighbor, something has been switching on and off, again and again, for nearly 2 decades. Each time it flares, it seems to leave behind a second, stranger signature. Ghost particles that pass through solid matter as if it isn't there, arriving from deep space, seemingly traced back to that exact same point of darkness. Astronomers expected Andromeda's black hole to be the quiet, predictable cousin of our own galaxy's monster. What they are finding instead is a core that refuses to sit still, hiding a history of violence beneath its calm exterior. So what is actually happening inside the object astronomers call M31, and why does it keep behaving like something is stirring inside it? To understand why this story matters, you first need to understand what Andromeda's black hole was supposed to be and how badly it has broken those expectations. Every large galaxy in the observable universe is thought to harbor a supermassive black hole at its center. This isn't speculation. It's one of the most consistent patterns astronomers have found while studying galaxies of every size and shape. Our own galaxy, the Milky Way, has one. It's called Sagittarius A, and it sits roughly 27,000 light-years from Earth, weighing in at a little over 4 million times the mass of our Sun. Andromeda's black hole, called M31, is a very different beast. It's roughly 100 million times the mass of the Sun, more than 25 times heavier than the black hole at the center of our own galaxy. On paper, that should make it the more dramatic, more active, more violent of the two. Bigger black holes, all else being equal, tend to have bigger appetites, and bigger appetites tend to produce more radiation as infalling matter is torn apart and heated before disappearing past the event horizon. But that isn't what astronomers observed, not for a very long time. Despite its enormous mass, M31 turned out to be one of the least active galactic nuclei ever studied. It wasn't blasting out jets of high-energy particles like the black holes found at the centers of quasars. It wasn't glowing brightly in radio waves the way many other active supermassive black holes do. By every conventional measure, it looked less like a monster and more like a slumbering giant, present, massive, but essentially dormant. Some astronomers have gone so far as to call it a starving black hole, technically confirmed to exist, but showing almost none of the violent feeding behavior expected of something its size. That mismatch, an object massive enough to be dramatic, behaving as if it were almost asleep, became one of the defining puzzles of Andromeda's core. And the first real crack in that quiet picture appeared decades ago, hidden in the temperature of the gas falling into it. In January of the year 2000, NASA's Chandra X-ray Observatory turned its instruments toward Andromeda for one of its first detailed studies of the galaxy. A team of scientists from the Harvard-Smithsonian Center for Astrophysics, led by researchers Stephen Murray and Michael Garcia, working alongside colleagues including Frank Permini, William Foreman, Christine Jones, and Ralph Kraft, examined the X-ray emission coming from the region immediately surrounding the black hole. What they found didn't match expectations. Material falling toward a supermassive black hole is normally expected to heat up dramatically as gravity compresses and accelerates it, reaching temperatures of many millions of degrees before it crosses the point of no return. But the gas Chandra detected near M31 was, by black hole standards, unusually cool, registering around 1 million degrees Celsius, far lower than the standard models of black hole accretion predicted for an object of this mass and environment. This wasn't a minor discrepancy. Dr. Elliot Quadert, an astrophysicist involved in interpreting the observation, noted that the findings suggested an entirely different flow pattern was operating around Andromeda's black hole, one that would require a different class of models than the ones typically used to describe supermassive black holes like the one in the Milky Way. In plain terms, the basic textbook explanation for how matter spirals into a black hole and heats up in the process didn't seem to apply cleanly to M31. Something about the way gas approached this black hole was fundamentally different from what theory predicted. At the time, this was treated as a curious anomaly, a puzzle worth investigating, but not necessarily evidence of anything dramatic happening at Andromeda's core. The black hole was still, after all, considered mostly dormant. It would take more than 2 decades, and a very different kind of observation, before the true scale of the mystery would begin to reveal itself. If the temperature of the infalling gas was the first sign that something didn't add up, the shape of Andromeda's nucleus was the second, and it was far more visually strange. In 1993, images captured by the Hubble Space Telescope revealed something astronomers weren't expecting to see. Instead of a single, smooth, symmetrical concentration of stars piled up around the central black hole, the pattern you'd expect from standard models of galactic nuclei, Andromeda's core showed 2 distinct blobs of light, offset from one another, nested inside a broader, lopsided ring of stars. This is not a subtle detail. A normal galactic nucleus is expected to be roughly circular and centered directly on its black hole, because gravity should pull stars into a fairly even distribution around the point of maximum mass. What Hubble showed instead looked almost like two separate structures sitting slightly apart from each other, off kilter, refusing to resolve into the clean, expected shape. It took years of careful follow-up observation to even begin making sense of what the images were showing. By around 2012, astronomers had determined that one of the two blobs, the blue one, was actually a compact disk of young, hot stars trapped in tight, fast orbits directly around the black hole itself. These stars were startlingly young by galactic standards, somewhere between 100 and 200 million years old, which is a small fraction of the age of the galaxy itself. The second blob, the redder one, turned out to be a separate, older, cooler population of stars arranged in a ring that was noticeably off-center from the black hole, roughly twice the size of the blue disk. Nothing like this exists in our own galaxy's center. The Milky Way's nucleus, while it has its own cluster of young stars near Sagittarius AST, doesn't show this same lopsided dual structure geometry. Andromeda's core is uniquely disturbed, and that raises an obvious question. What kind of event could leave a galactic nucleus looking like this? One of the more compelling explanations proposed by astronomers involves an ancient, violent event, a black hole merger. Galaxies grow, in part, by colliding and merging with other galaxies over cosmic time, and when two galaxies merge, their central black holes are often drawn together as well, eventually spiraling in and merging into a single, larger black hole. When two black holes of significant but unequal mass collide, the resulting merger doesn't necessarily settle quietly. According to some models, the merger can produce a kick, a burst of gravitational recoil that sends the newly combined black hole moving relative to the surrounding stars, potentially displacing it from the exact center of the galaxy and disturbing the orbits of stars nearby. If something like that happened in Andromeda's past, it could help explain both puzzle pieces at once: the off-center placement of the young stellar disk and the broader lopsided ring of older stars surrounding it, disturbed by the aftermath of an ancient collision. It's an elegant hypothesis, and it's taken seriously by researchers studying Andromeda's structure. But it remains a hypothesis. Nobody observed this merger directly. If it happened, it would have occurred long before any human telescope existed. What astronomers have is the aftermath: two blobs of light that don't fit the standard picture, and a plausible but unconfirmed explanation for how they got that way. And Andromeda's core had one more surprise waiting, discovered not in ancient starlight, but in a nearby cluster of stars that turned out to be something else entirely. For a long time, a compact object near Andromeda's core, known as B023G-38, was classified simply as a globular cluster, a dense, spherical grouping of old stars, the kind of structure found orbiting most large galaxies in fairly large numbers. Nothing about that classification seemed particularly remarkable. Then, in a study reported in early 2025, researchers proposed a very different identity for it. Rather than being an ordinary star cluster, they argued that B023G078 is instead what's known as a stripped nucleus, the surviving core of an entirely separate, smaller galaxy that was consumed by Andromeda long ago. According to this interpretation, the smaller galaxy's outer layers of stars and gas were torn away by Andromeda's much stronger gravity during the encounter, a process called tidal stripping, leaving only the dense, compact central remnant behind, still orbiting within Andromeda's halo like a fossil. This finding matters for reasons that go beyond a single object's reclassification. If confirmed, it means that smaller galaxies absorbed by a larger one don't necessarily need to carry a full-sized supermassive black hole at their center in order to leave behind a permanent, identifiable structural remnant. Their naked stellar cores alone can survive the process, drifting through the halo of the larger galaxy long after the rest of the smaller galaxy has been dismantled. That reframes how astronomers have to think about Andromeda as a whole. This isn't simply a single, self-contained galaxy that grew in isolation. It's a survivor of repeated collisions and mergers, a graveyard of absorbed neighbors, each one potentially leaving behind its own structural fingerprint scattered throughout the galaxy's core and halo. Untangling which strange feature near Andromeda's center belongs to which cannibalized history, the double nucleus, the stripped remnants, the disturbed stellar populations, is part of what makes this particular galaxy's core so difficult to interpret cleanly, and part of why new discoveries keep complicating a picture astronomers thought they understood. With that context in mind, a black hole with unexpectedly cool infalling gas, a nucleus scarred by what may have been an ancient collision, and a halo littered with the remains of smaller galaxies, the stage was set for the most recent and arguably most startling chapter in Andromeda's story: real-time evidence that its black hole has been flaring repeatedly for nearly 2 decades. For years, Chandra had been quietly collecting X-ray data from the direction of Andromeda's core, largely as part of broader ongoing observation programs. Buried within that long-running data set was a story nobody had fully pieced together, until a researcher named Stephen DeKirby, working at Michigan State University alongside collaborators Shojang and Jimmy Irwin, decided to take a comprehensive second look. DeKirby and his team set out to extend an earlier analysis of Andromeda's black hole, originally conducted by researchers Jiwon Lee and colleagues, by adding an additional 15 years of Chandra observations, spanning from 2009 through 2024. Their goal was to build the most complete X-ray light curve of M31 once ever assembled, essentially a long-term brightness record, tracking exactly how much X-ray light the black hole was emitting and when. This is a genuinely difficult technical challenge. Andromeda's core isn't home to just one X-ray source. It's crowded with several distinct emitters sitting close together, including sources the team labeled S1, SS, and N1, alongside the black hole itself, designated P2. Separating the black hole's specific signal from its noisy neighbors required Chandra's exceptionally fine spatial resolution, the ability to distinguish separate points of light that would blur together into a single blob using almost any other X-ray telescope currently in operation. What the team found, once they had isolated M31's own signal, was striking. Rather than showing the steady, low-level emission expected of a mostly dormant black hole, the data revealed a major X-ray flare that occurred in 2006, a dramatic temporary spike in brightness. Even more notably, the black hole didn't simply flare and then return to its previous quiet state afterward. Instead, following that 2006 event, M31 settled into a sustained, measurably elevated state of X-ray activity that, according to the data, persisted through at least 2016 when regular Chandra monitoring of the region ceased. A second, more moderate flare was identified in 2013, standing out clearly because the other nearby X-ray sources happened to be in unusually low brightness states at the same time, making that particular flare an especially clean signal to study. There's a gap in the data between 2016 and 2021 when the region wasn't being monitored as consistently. But observations picking back up from 2022 onward suggest the elevated state may still be ongoing, with the most recent data available to the researchers still showing X-ray flux above the black hole's earlier baseline. Because of that observational gap, the team can't say with certainty whether the currently elevated brightness is simply the long tail of the original 2006 flare, still fading slowly nearly 2 decades later, or whether additional undetected flares occurred during the gap and are contributing to what's being measured now. DeKirby described the moment of realizing what the data showed in strikingly personal terms, saying that after analyzing the observations, he felt a chill, because he understood he was looking at direct evidence of a supermassive black hole flickering on and off, captured in extraordinary long-term detail. It's worth pausing on why that reaction makes sense. Supermassive black holes evolve on timescales that dwarf a human lifetime. Catching one in the act of flaring, not once, but at least twice, with a sustained behavioral change lasting years afterward, is a rare and valuable window into physics that normally unfolds far too slowly, or too rarely, for scientists to observe directly. The team also examined something called the hardness ratio of the black hole's X-ray emission, essentially a measure of whether the X-rays being produced skew toward higher or lower energy levels. Interestingly, they found that the hardness ratio during the 2013 flare was roughly consistent with the hardness ratio measured during the black hole's non-flaring periods, a detail that offers a clue about what kind of physical process might be driving the flares, even if it doesn't yet provide a definitive answer. On its own, a flaring black hole isn't necessarily a deep mystery. Supermassive black holes are known to flare occasionally, usually attributed to clumps of infalling gas, or, in some documented cases elsewhere in the universe, to the tidal disruption of a star that wandered too close and was torn apart by gravity. What makes M31's flaring pattern worth a much closer look is the company it appears to be keeping, a second entirely different kind of signal that seems to be arriving from the exact same point in the sky at suspiciously similar times. To understand why this second signal matters so much, you need to understand what a neutrino actually is, and why detecting one from deep space is such a remarkable technical achievement. Neutrinos are subatomic particles with almost no mass and no electric charge. They interact with ordinary matter so weakly that trillions of them pass through your body and through the entire planet Earth every single second, almost entirely unnoticed. Scientists sometimes call them ghost particles for exactly this reason. They can travel through solid rock, through stars, through entire planets, and barely register an interaction at all. That property makes them incredibly difficult to detect, but it also makes them incredibly valuable scientifically, because unlike light, neutrinos aren't blocked or scattered by the dust and gas that fills galaxies. A neutrino that reaches Earth's detectors has, in a real sense, traveled in a straight line from wherever it was produced, carrying direct information about violent, high-energy events happening deep in space. Detecting these particles requires massive, specialized observatories, and tracing a detected neutrino back to its point of origin. In the sky is an extraordinarily difficult task, given how rarely they interact with anything at all. Despite that difficulty, one of the world's leading neutrino observatories, IceCube, a detector buried deep in the Antarctic ice, has, in other cases, successfully linked bursts of neutrino detections to X-ray flares occurring in specific, distant, active galaxies. That established pattern, seen elsewhere in the universe, is what made Andromeda's own flaring black hole worth investigating from a completely different angle. De Kirby, who is also a member of the IceCube Neutrino Observatory collaboration, wanted to know whether M31 might belong to this same category of object, a supermassive black hole capable of producing high-energy neutrinos alongside its X-ray flares. According to reporting on the study, the investigation into Andromeda's black hole activity was prompted in part by neutrino detections that, when traced, appeared to point back toward the direction of M31, arriving in a way that lined up with the black hole's known periods of elevated X-ray activity. This is where scientific caution becomes essential, and where the difference between a documented correlation and a confirmed discovery really matters. Tracing a single neutrino detection back to one specific galaxy, out of the enormous number of galaxies scattered across the observable sky, carries real uncertainty. A neutrino's trajectory can be measured, but not with perfect precision, and there are countless potential sources scattered along any given line of sight. What researchers have identified is a pattern, a timing alignment between X-ray flares from M31-1 and separately detected neutrino events, that mirrors a relationship already documented in other, more distant active galaxies. It is not, on its own, definitive proof that Andromeda's black hole is the confirmed source of any particular neutrino. But patterns like this are exactly how major astrophysical discoveries typically begin. Correlation isn't causation, but a correlation that's statistically unlikely to be coincidental, and that matches a mechanism already seen working elsewhere, is precisely the kind of clue that drives further investigation. If the relationship holds up as more data accumulates, more flares from M31, more neutrino detections traced to the same patch of sky, more careful statistical analysis ruling out chance alignment, it would mean something genuinely significant, that our nearest large, supermassive black hole, long dismissed as one of the quietest, least active examples known, has been capable, at least periodically, of accelerating particles to some of the most extreme energy levels found anywhere in the universe. To appreciate how strange this combination of findings really is, it helps to step back and picture the standard, textbook model of a quiet, supermassive black hole. In that model, a black hole like M31 Ton sits at the center of its galaxy, slowly accumulating gas from a broad, relatively calm accretion disk. Material spirals inward gradually, heating up in a smooth, predictable way as it approaches the event horizon, releasing a steady, low-level glow of radiation across different wavelengths. Nothing about this picture involves dramatic flares. Nothing about it involves the kind of extreme particle acceleration typically associated with neutrino production. It's a picture of gradual, almost boring consumption, which is exactly the behavior astronomers originally expected from Andromeda's black hole, given its historically low activity levels. Every piece of evidence uncovered over the past 2.5 decades chips away at that simple picture. The unexpectedly cool temperature of the infalling gas, first measured in 2000, suggested the accretion flow around M31 didn't match standard models to begin with. The lopsided dual-structure nucleus revealed by Hubble suggested a violent disturbance in the black hole's relatively recent history, possibly an ancient merger, still leaving its mark on the surrounding stars today. And now, the 15-year X-ray record assembled by De Kirby and his team reveals a black hole that isn't simply glowing steadily, but flaring dramatically, settling into new elevated states that persist for years, and possibly producing some of the highest energy particles known to physics along the way. Individually, each of these findings might be explained away as an isolated anomaly. Together, they paint a much more coherent and much more unsettling picture. Andromeda's supposedly quiet black hole may have a far more violent and complicated history, and present, than its outward reputation as a starving, inactive giant would ever suggest. None of this means M31 is secretly some undiscovered new category of astrophysical object. No credible researcher studying the system is making that claim, and the evidence doesn't support it. Supermassive black holes are well-established, well-understood objects in general terms. What these findings suggest instead is something almost more interesting, that even a well-studied, seemingly ordinary supermassive black hole sitting close enough for detailed, decades-long observation can still behave in ways that don't fit the simplified models built to describe it. It's worth being precise about exactly what has and hasn't been established here, because the honest scientific picture is more interesting than an exaggerated one. Confirmed. Andromeda's black hole underwent a documented X-ray flare in 2006, followed by a sustained period of elevated activity, and a second identifiable flare in 2013. This comes from a peer-reviewed analysis of 15 years of Chandra X-ray data, published in the Astrophysical Journal in 2025. Confirmed, the infalling gas near M31, as measured by Chandra in 2000, showed an unexpectedly low temperature compared to standard black hole accretion models. Confirmed, Andromeda's nucleus contains two distinct stellar structures, a young blue stellar disk and an older off-center red stellar ring, first revealed by Hubble imaging in 1993 and further characterized in subsequent studies. Proposed but not confirmed, that the double nucleus resulted specifically from an ancient black hole merger and gravitational recoil kick. This remains a leading hypothesis, supported by modeling, but not a directly observed event. Proposed but not confirmed, that the object at B0230 G078 near Andromeda's core is a stripped galactic nucleus rather than an ordinary star cluster. This interpretation was put forward in research published in early 2025 and adds context to Andromeda's history of galactic mergers, but represents one team's analysis rather than settled consensus. Suggestive, but unconfirmed. A timing correlation between M31's X-ray flares and neutrino detections traced back toward Andromeda, echoing patterns seen in other active galaxies studied through IceCube. This connection is actively being investigated, and researchers themselves describe it as a pattern worth further study, not a confirmed causal link. Laying it out this way doesn't diminish the mystery. If anything, it sharpens it. This isn't a story built on exaggerated claims or invented data. It's a story built entirely on real, peer-reviewed, carefully measured observations, each one individually modest, but collectively pointing toward a black hole that keeps behaving in ways its own discoverers didn't originally expect. There's a reason astronomers keep returning to M31 West, pouring years of Chandra observation time into studying it in this much detail. Proximity. At roughly 2.5 million light-years away, Andromeda is, by cosmic standards, essentially next door. It's the nearest large spiral galaxy to our own, similar in overall size and structure to the Milky Way, and close enough that telescopes can resolve fine details near its center that would be completely invisible in more distant galaxies. Most of the supermassive black holes previously linked to high-energy neutrino production through observatories like IceCube are found in far more distant, more obviously active galaxies, places already known for dramatic, energetic behavior. Andromeda was never supposed to be one of them. It was supposed to be the calm, well-behaved control case, useful precisely because it wasn't expected to do anything dramatic. That's what makes these findings so significant, beyond the specific details of any single flare or hypothesis. If a black hole this close, this well-studied, and this historically quiet turns out to be capable of extreme, high-energy behavior, it raises an uncomfortable question about every other supposedly dormant, supermassive black hole scattered throughout the universe. How many of them are genuinely inactive, and how many are simply behaving the way Andromeda did for decades, quiet in every measurement astronomers happened to take, until someone finally looked at the right data over a long enough span of time to catch it in the act? De Kirby, reflecting on the significance of the research, expressed hope that the study would encourage other scientists to continue analyzing data from M31, emphasizing the importance of maintaining the aging Chandra telescope while plans for future observatories continue to develop. His stated goal, in his own words, was to keep watching the system, to keep watching for further flares, and to continue writing the ongoing history of supermassive black holes as that history unfolds in real time. That's a strikingly modest way to describe what may turn out to be a genuinely significant discovery, but it reflects how real science actually works, not through single dramatic reveals, but through patient incremental observation, extended year after year, until a pattern emerges clearly enough to warrant a closer look. The story of M31 Wayne isn't finished. It's arguably just entering its most interesting phase. Researchers are continuing to monitor Andromeda's black hole for further X-ray flares, hoping that future observations, combined with ongoing neutrino detection efforts through IceCube, will either strengthen or break the tentative link between M31's flaring behavior and high-energy particle production. A single additional precisely timed flare, one that coincides clearly with a fresh, well-measured neutrino detection, could dramatically shift this story from an intriguing correlation to a confirmed source, fundamentally changing how astronomers think about black hole activity in otherwise ordinary-looking galaxies. There's also the open question of what happened during the observational gap between 2016 and 2021, when Chandra's monitoring of the region became less consistent. Filling in that gap, whether through reanalysis of existing archival data or through new, more consistent monitoring going forward, could reveal whether Andromeda's black hole experienced additional flares that have simply gone undetected so far. flares that might refine or complicate the current 15-year picture even further. And there's the broader question raised by the reclassification of objects like B023, G078. How many other structures scattered throughout Andromeda's halo are similarly fossil remnants of long-consumed smaller galaxies waiting to be correctly identified? Each new reclassification adds another layer to the story of how Andromeda became the galaxy it is today, and how its central black hole ended up with the strange, disturbed nucleus astronomers now observe. Step back and consider the full arc of what's actually been established here, using nothing but confirmed, peer-reviewed observations spanning more than 2 decades. A supermassive black hole, initially believed to be one of the quietest, most dormant examples known, was found in the year 2000 to have unexpectedly cool and falling gas, hinting that its accretion process didn't match standard theoretical models. Its surrounding nucleus, imaged by Hubble in 1993, turned out to be split into 2 mismatched stellar structures, a lopsided scar most plausibly explained by an ancient, violent merger that nobody directly witnessed. Its wider halo contains at least one object recently reclassified as the stripped, surviving core of a separate galaxy that Andromeda consumed at some point in its deep past. And now, a 15-year X-ray record has revealed that this same quiet black hole underwent a major flare in 2006, settled into a new, sustained elevated state that may persist to this day, experienced a second flare in 2013, and appears, tentatively but intriguingly, to be linked to bursts of high-energy neutrinos arriving from the same direction in the sky. None of these findings, taken alone, would justify calling Andromeda's black hole impossible. But taken together, they describe an object that has spent the better part of 30 years quietly overturning the assumptions astronomers originally made about it, not through a single dramatic anomaly, but through a slow accumulation of evidence that keeps pointing in the same unsettling direction. This black hole has a far more violent past, and possibly a far more energetic present, than its reputation as a sleepy, starving giant would ever suggest, which leaves an open question hanging over everything scientists have found so far. If the calmest, closest, most thoroughly studied supermassive black hole in our corner of the universe has been quietly producing some of the highest energy events known to physics, and doing it for the better part of 2 decades before anyone fully pieced the pattern together, well, what does that say about every other black hole assumed to be genuinely dormant, sitting undisturbed at the center of some distant, ordinary-looking galaxy nobody has thought to watch this closely? Andromeda was supposed to be the safe, predictable case study, the calm control group against which more dramatic black holes could be measured. Instead, it has become a quiet warning that inactive and quiet, in the language of a supermassive black hole, might not mean what astronomers once assumed, and that the next flare from its core, whenever it arrives, could finally reveal which explanation has been right all along.